So today our goal is to learn the different types of chemical reactions. There are 5 we're going to talk about. So you can see some of them on the board there. Synthesis, decomposition, single displacement, double displacement. And we're also going to talk about combustion, the 5th type, which is why we're going to combust the gummy bear today. We're going to look at 3 kinds of synthesis reactions and actually 6 different decompositions, 4 kinds of single displacement, and 3 kinds of double displacement. I'm not expecting you to recognize each of those types of those reactions, but I do want us to know the general 5, the main 5, the synthesis, decomposition, single and double displacement, and then combustion. And eventually we get to the point where we could even predict what the reactants are going to be once we have a good understanding of those types of reactions. So here they are. I already said it, but synthesis, decomposition, single displacement, double displacement, and combustion. And we'll have a basic layout for what each of those looks like. First one, synthesis. Valentine's Day coming up. We have some interesting love stories, I guess. The first one, the synthesis, is kind of your most basic, like Hallmark movie type love story. You've got 2 single elements or compounds. One is A, one is X. They come together, they form AX. They live happily ever after. AX. A is for the city, he goes to live in a small town.
Like cutting board man that lives in a small town, and then they fall in love and live happily ever after.
See, you're going with it. I like that. They live happily ever after. Yeah, I should have put a picture of that in there, like what you're describing, some kind of Hallmark movie. But the specific example. So yeah, what'd you say? Magnesium's from the city and ends up moving to the country or whatever. But magnesium is a single element. Oxygen, even though it's a molecule, we're going to still consider it a single entity. And they join together, magnesium and oxygen, to become magnesium oxide. Group 2 elements react in a similar way, where they form that MO, meaning a 1-to-1 relationship between that metal and oxygen. On the other hand, group 1 metals will form oxides with the formula M2O, just like H2O. We've got Li2O, anything in group 1, Na2O. This also happens with sulfur, because sulfur, like oxygen, has a -2 charge. So group 2 elements will form sulfides, like M2S and MS, group 1 and group 2 respectively. So my example there, rubidium can form with a molecule of sulfur, form rubidium Rb2S, and then barium is a group 2. It can form with sulfur and form BAS. 1-to-1 relationship there. Metals tend to react with the group 17 halogens to form ionic or covalent compounds. Another example, we could have pure sodium combined with pure chlorine gas. They come together and they form sodium chloride. Another example with group 2, we could have magnesium joins with fluorine to become magnesium fluoride. So MgF2, because the group 2 elements will form an MX2 combination there. When I say active, I mean that the metal is highly reactive. So oxides of active metals react with water to produce metal hydroxide. So an example would be calcium oxide will react with water. So notice this is two compounds coming together. It doesn't always have to be an element. Two compounds, calcium oxide and water, form together to become calcium hydroxide. So those are all synthesis reactions. Notice the key, a lot of times what helps you to figure this out, look for the plus sign on the left, no plus sign on the right. You had more than one thing on the left, only one thing on the right. Same with these two. Notice I've got two entities becoming one, two entities becoming one. It could be three entities becoming one. But the oxides of nonmetals react with water to produce oxyacids like sulfuric acid. So that's synthesis. Any questions on synthesis? So then, now we have the SAD. So that we had the Hallmark movies, but now we have the SAD, the breakup movie. We've got the compound. They don't last very long. They end up breaking up. A and X were together. Now they're separated as A plus X. Now they're their own thing. Maybe they're happier that way. In chemistry, they are happier that way. But the example we looked at the beginning of the year was breaking down water. We broke down water into its individual components, hydrogen and oxygen. And we used electricity through what's called electrolysis. And notice this is exactly the opposite of synthesis. Synthesis, I'm synthesizing, I'm putting things together. It's also called a composition reaction, like a composer makes something new, they compose something. When I decompose something, I'm breaking it apart, right? When something's decomposing, it's breaking down. I have a reaction here with mercury oxide. Mercury 2 oxide to be specific. And it's going to decompose into mercury and oxygen. So I've got the mercury oxide here. And it's red substance. What would you expect to look like if it decomposes into pure mercury and oxygen? Yeah, it's going to be like a blackish mercury thing. And then they were creative here. They put a tube all the way into some water. And so we're going to see the oxygen bubble up in there.
Classic experiment of Lavoisier. Mercury oxide is heated.
Notice I need to heat it.
Metal and oxygen gas. In a test tube, we have a sample of red mercury 2 oxide. We will heat the sample and it will decompose to give mercury metal, which will condense at the top of the test tube, and oxygen gas, which we will collect by the displacement of water.
So see the oxygen 2 bubbles that we recognize.
The mercury metal we can see as a metallic gray ring in the test tube. We can demonstrate that the gas collected is oxygen.
Anybody have a guess what's going to happen when the oxygen, when he puts the flame in the oxygen? Yeah, it's going to, well, maybe not that extreme, but yeah, it's going to,
as the glowing splint is brought into the
encourage
test tube,
the flame.
The combustion accelerates in the oxygen and the splint reignites.
So we'll actually do a lab where we test for oxygen gas, hydrogen gas, carbon dioxide gas, and you'll see carbon dioxide would do the opposite. It would put the fire out. That's why they use the fire extinguishers with carbon dioxide. So then the hydrogen will ignite. So that's my heating to break down the mercury oxide into its individual components. Again, just a bunch of examples of decomposition reactions. for example, if I decompose a metal carbonate, and these are the three gases we're going to test for in lab, but if I decompose the metal carbonate, I get a metal oxide with carbon dioxide. If I decompose a metal hydroxide, I get the metal oxide with water. And if I decompose a metal chlorate, notice they use heat and they use the catalyst to speed that reaction up, the MnO2 there. So then if I decompose potassium chlorate, I get potassium chloride and oxygen. So those are how I can break down things to get those three gases. I can break down carbonates, I can break down hydroxides, I can break down chlorates to get chlorides, oxides, and then those three gases I mentioned. We also see this in acids. Acids can decompose into non-metal oxides in water. So for example, carbonic acid is unstable and will decompose to produce carbon dioxide and water. As you can see in the equation there, H2CO3 will become CO2 and H2O. So that was decomposition. So keep a track over there. We had synthesis, we had decomposition. Now we've got single displacement. And single displacement is a little bit more interesting as a love story here because we have a single entity and then a happy couple over here, the BX. A is actually going to come along and steal X from B, so now the new couple is AX, and now B is left all by its lonesome. It doesn't always have to be the metal that steals the non-metal. You could also have a non-metal stealing another non-metal away from the metal. In that case, I would have Y and BX, but then afterwards I have BY and X. So that's my single displacement reaction, or single replacement. Sometimes you hear it called. I am looking at, usually these are happening in aqueous solutions. You can pour two solid substances on each other and have this happen. It's going to take a long time. Being in water sort of encourages those reactions to take place at a faster rate. But notice these are, the single ones are all elements, and the pairs are all compounds. So aluminum is there, and you've got lead 2 nitrate. Unfortunately, lead 2 nitrate's relationships on the rocks. Aluminum comes along, Mr. Stereonitrate, and takes the lead away, or takes the nitrate away from the lead, and you have lead and aluminum nitrate. Does that make sense, the gist of the single displacement? So then you can also see it with like hydrogen. We have sodium is by itself, and we saw this reaction. That's the one that we watched, the sodium with the water. Sodium will replace the H2, and you saw me cleaning off the glass. That was all that sodium hydroxide, and you had hydrogen gas. Less active metals might react with steam, like iron can react with steam to form metal oxide and hydrogen gas. In fact, I'm going to look that up. Whoops. Iron and steam. I don't want to steam with an iron. I want the chemical reaction. See magnesium with steam. Here we go. try this. So this is an animation, I guess. Because iron, if you just put it in cold water, it won't react. But we heat it up. We see hydrogen form. And the hashtags are all covering up the iron down there. You can't even see it. But we basically get iron oxide. And that's the reaction. Iron 3 oxide. Wish I had a better... I didn't see a better video to show that. But the other one there, like I said, halogens can also replace, nonmetals can also replace nonmetals. So in this case, you have some halogens like chlorine stealing away potassium. So chlorine comes along, steals bromine's potassium. So now bromine's left to fend for itself. The second reaction, fluorine, comes along, replaces the chlorine, and now you have NaF in chlorine. But notice that doesn't always happen. Obviously, if it always happened, then this would just go back to being this, right? And then this would go back to being this. There has to be a reason for the reaction to happen. And what that reason is chlorine is more active than bromine on the table. Fluorine is more active than chlorine. However, bromine is not reactive enough to take away chlorine. So bromine has to just stay. Poor bromine seems to always get left alone because it's one of the least reactive halogens. It always either gets replaced or doesn't react. So that was single displacement. Double displacement is even more interesting because now you've got two pairs and they switch partners. So double displacement reaction. You have the ions literally swapping places. And usually we're going to see a precipitate form. So in lab, we're going to do a lab where we observe a well plate and we try different compounds mixed together and see which ones form a precipitate. You usually have one that's soluble and one that's not soluble. One that dissolves and one that forms a precipitate. But here's the general form for a double displacement. Now you have AX plus BY becomes AY plus BX. The classic example I see a precipitate form is you get lead 2 iodide when you mix a solution of potassium iodide and lead 2 nitrate. And you'll see this in lab. You mix them together and you end up with a precipitate of lead 2 iodide and potassium nitrate. Time to show you that reaction real quick. Let's see here. So here you have your potassium iodide solution, and then you have some lead nitrate. Actually, did they? Yeah. Notice how it's forming a precipitate there. That yellow stuff is your lead 2 iodide. What's cool is if you heat it up enough and let it cool down, it'll crystallize. I think this is a time lapse. And then it makes those yellow crystals in there over time. Eventually it looks like that. But that's an example of where you have a precipitate forming from two solutions. Here we have an example of a formation of a gas from double displacement. We have iron 2 sulfide with hydrogen chloride. And a lot of times what helps with these double displacements, the inner ones will form together, and then the outer ones will form together. So here we have H and S making H2S, and then FeCl making FeCl2. We can also have water form. So classic one, hydrochloric acid and sodium hydroxide. I can make table salt because the NaCl forms a solution. And then the outer one, this might not be as obvious, but HOH is just water. If I have hydrogen hydroxide, HOH, that's just the same thing as H2O. It's two H's molecularly combined with an oxygen. So those are a couple examples of double displacement. And then finally, we've got our combustion, which we'll look at combusting a gummy bear. In a combustion reaction, a substance combines with oxygen, releasing a large amount of energy in the form of light and heat. So with combustion of hydrogen, we have H2 and O2. Notice this looks a lot like a synthesis reaction. So like I said, not every reaction is going to be cut and dry. Sometimes you have some gray area where it can sort of be both. It can be a synthesis reaction and a combustion reaction. But notice the key here is you've got that oxygen. Usually you see something burning in oxygen. And then classic combustion of propane, any hydrocarbon like propane you're going to see CO2 and H2O. On homework 8A, you probably saw a lot that had CO2 and H2O. Those are usually combustion reactions. So that's one thing I always look for first is if there's CO2 and H2O, I know that's a combustion reaction. We're actually going to combust a gummy bear. I don't think that one. Yeah, these ones are a little beyond what we're doing right now, so we're not going to look at those. But we are going to combust the gummy bear real quick.
And this is what happens when you drop it into boiling potassium chloride. Whoa, that was awesome. But we're VAT-19, and this is the world's largest gummy bear. So... Find the 5-pound gummy bear and hundreds more curiously awesome products.
I think that's just an ad. But yeah, those are the 5 types of reactions: synthesis, decomposition, single displacement, double displacement, and combustion. And we'll go over those a little bit more tomorrow or Monday, and then practice identifying them.